just wanted to thank you both for participating to this, and I'm really glad that you can share your long experience on the safety domain. I'm really looking forward to see. And John, Jason, I think you can share with the audience how you'd like to handle. If you'd like to have questions in the middle or wait till the end, that's up to you. So thanks again for for organizing this, for doing this, and giving your time to this.
Great. Well, I guess we'll get started. So I'm John Hayden, the Automotive Functional Safety Manager at Analog Devices, and Jason Campbell is going to be my co-presenter. And the way we're going to do this today is I will provide background and overview of our tutorial on functional safety analysis and verification. So I'll give you an idea of what safety is, what the safety verification and analyses are, and when we do them and why we do them. And then we'll break for questions, and then Jason Campbell here from NVIDIA, my co-presenter, will dive into the detail, again with some time for questions at the end. So let's get to it. So what is functional safety? For those that haven't done this before, functional safety is safety is generally defined as freedom from unacceptable risk. And in engineering, risk isn't completely eliminated. Some very small risk is acceptable according to society's ethical and moral norms. Now, functional safety is the kind of safety when you achieve that by adding active safety functions like monitors or redundant signal chains, as opposed to passive safety like protective covers or fire safety. And there's a whole set of functional safety standards in various industry segments that you can see on my slide here, going back to the industrial and aviation core. But today we're going to be talking about automotive functional safety. So what is automotive functional safety? So this applies to electronic systems in vehicles and road users. So that's cars as well as vans and trucks and motorcycles. It includes the electronic elements down to the modules and the ICs and the hardware and the software that's involved. Now, what does functional safety mean? So the standard defines this as the absence of unreasonable risk due to hazards, meaning injury to persons, caused by malfunctioning behavior of electronic systems. So in short, what this means is we do this so that our handiwork doesn't kill people. That's our sacred trust as developers, as engineers. We recognize that we're developing systems and components that can malfunction and will malfunction during their lifetime and still have to achieve a safe state in these products. And we commit to follow this standard life cycle to achieve the level of safety integrity needed to allow hundreds of thousands of families to put their trust in us. That's why we do this. And if you're not ready to assume this responsibility, feel free to go design something else. But this is what it takes to work in automotive safety. Now, safety integrity is a property of a vehicle level system, not really of an individual component. And only in the context of that system can you determine what the safety requirements on its elements need to be. So for instance, if we've got an electronic power steering system, the maker of that must identify the possible malfunctions of their product and analyze them to see if they could create a hazard, such as, if a steering angle sensor error might lead to unintended steering and cause a harm such as an injury due to a crash. So it helps to compare what we do for functional safety with other kinds of verification activities, such as functional DV at manufacturing test and cybersecurity. So each of these activities might include what we call verification, but they have different goals. In functional DV, our goal is to prevent bugs. In other words, flaws in the systematic design that prevent the product from achieving its goals. And that only happens in the design phase where we run simulations or put perhaps DFV features in the product. And we also do manufacturing outgoing test where we have a different goal, which is to detect defects where the article that's been manufactured does not match its specification. And we only get to do that when it's in the factory. once it's left the factory, it's out of our hands. And we do things like scan test and functional test and include DFT features in our products. But on the right here, functional safety and cybersecurity happen through the whole life cycle of the product. After it's left the factory, when it's being installed, manufactured at the customer and in the car over many years, and even into decommissioning. And the goals here are somewhat different. The goal for functional safety is to prevent a malfunction from causing a hazard. And we don't really care about the details of it. We just make sure that the system becomes safe. We don't care about debug at this stage, for instance. We do this through innovating safe architectures and adding safety mechanisms. Cybersecurity is somewhat similar, but here the goal is to prevent attacks on assets. And unlike random hardware faults, which might happen here or there randomly, once a vulnerability has been discovered in cybersecurity, it will happen very intensely over and over until real-time incident response teams can prevent it. But again, we mitigate this with secure architecture, security mechanisms, and response teams. So let me give you an idea of the basic functional safety workflow. It's fairly familiar. You're going to identify hazards that might occur, and you're going to rank them due to their dangerousness by this ASIL, or Automotive Safety Integrity Level rating, from A to D. And you're going to define safety goals to prevent them, and then allocate safety requirements from the vehicle level on down through your Tier 2 module, your Tier 1 module, your Tier 2 IC, and your Tier 3 IP providers. And then everybody designs their element to meet those requirements and verifies it on the way up. And then at the top level, the vehicle maker, the OEM, is going to validate on a test track that it actually achieves functional safety. And all along the way, you show your homework. In other words, you create evidence through everyday work with work products that you can keep for years afterwards to show that the system process was followed. But most ICs aren't really designed this way. We don't start at the vehicle level and work our way down. We do this design what we call out of context, where we speculatively identify some market need, we develop a product to address that. And so we've tailored the process into this part in the blue rectangle here, where we document our assumptions as to what we expect the safety requirements are going to be, develop and verify to that, and produce our evidence as semiconductor providers or module providers that are then used by the next level up integrator in their safety case. So what's critical is that there's a good package of documentation that shows what the assumptions were that they can verify against, along with the safety requirements they must follow and the safety analyses. And that all is called the safety case. Now, it has to be said that safety has to be baked in from the start. You can't easily test to this end at the end as some sort of paperwork exercise. So it's best done by innovating safe architectures, say some type of redundancy or comparators or other mechanisms that always can bring a malfunctioning system to a safe state. Now, what you do is you start by creating your proposed architecture and then analyzing it before you build it with qualitative analyses, and iterate until you have an expectation that the architecture is going to be solid. Then you go build it, and then you do second round of safety analyses with numbers to show that you've met the target metrics. And I'll talk about those metrics in a moment. So the safety analyses can take a few different forms in order to discover what these safety requirements might need to be. One is from the top down, what we call a fault tree, where you identify some top level failure, like violation of a safety goal, and you identify the faults that might give rise to it. And then you're going to place safety mechanisms in the system, which are shown as an AND gate, because it takes a failure of both the safety mechanism itself, hopefully small rate, together with a primary function to now cause the failure. A fault tree is also a really good way of determining if you've got common cause faults that might bring down both your safety mechanism and your primary function. And typically these are faults in, say, your clock tree or your reset or your power supply or shared references and so forth. Now, another class of safety analysis is the FMEA or FMEDA, which starts as bottom up. You take your system, you break it down into components, and I enumerate all of the potential faults and failure modes of those low-level elements. And then I figure out how they're all going to combine to contribute to top-level faults or violation of safety goal. Now, in safety, then what you're going to do is you're going to line up safety mechanisms for the most significant of these failure modes and evaluate their failure rates and diagnostic percent coverages of how effective they are at controlling these faults, and then evaluate your overall metrics. Now, a third and important type of analysis of a system is to look at it as a whole control loop, which we do in STPA, which I think is Systems Theoretic Process Analysis, where you look at some underlying process in hardware, such as electronic steering and its control unit. But you also even include the operator, recognizing that all forms one big control loop, that all must be functioning properly in terms of the messages going down, like control actions of the driver, the steering control to the ECU, to the rack, and then feedback coming back from sensors and displays. And all of this has to be functioning in order for the system to be stable and maintain its intended state. So in STPA, what you do is systematically go through all of these messages looking for, say, incorrect feedback from a sensor or unsafe control actions with an unintended actuator message, and then evaluate all of them to see if it might lead to a loss. And here I'll just briefly show some screenshots of some of these analyses, such as an FMEDA, where a system is broken down into its component elements. Their failure modes and failure rates are enumerated, where the failure rates in per unit hour calculated from mission profile and maybe the silicon area involved. And then they're evaluated to see which of these could lead to a violation of a safety goal. And here, the safety goal, known or assumed, is always the North Star in our safety analyses. We always have to have that in mind, otherwise it doesn't really work. And that allows you to always have an unambiguous reference as to whether something is going to be safe or not. And then for the things that do require attention, you can line up safety measures for both single and multi-point faults. And then similarly, we talked about a fault tree, and here's an example of that, showing the OR and AND gates and the determination of the overall failure rate, which is best done in a fault tree. Now, now we can look at how these faults affect the system, because functional safety is all about controlling malfunctions caused by faults. So it's important to say, what do we mean by that? Now, these come in two different categories: systematic faults and random faults, random hardware faults. And systematic faults are faults in the design process, design bugs, maybe because of weaknesses in the CAD tools or in the engineering department workflow. But most importantly, they all stem from some flaw in the workflow that's not controlled by its oversight controls, and they can affect both hardware and software. Random faults, on the other hand, only apply to hardware, and oddly, you might counterintuitively, they are predictable. Random faults can be estimated based on the properties of the materials that are used, such as corrosion or VT shifts through life, stresses, particle strikes, and come in both permanent faults, such as shorts and opens, as well as transient, like bit flips. Note that we have to consider both permanent and transient and systematic and random faults in our analyses. And again, software is only considered to be systematic faults. Software doesn't fail randomly. Faults in software are viewed to be flaws in the design process of the software. Now, let's look at how faults affect the system. In safety work, we always classify them as to whether they are either a single point or multi-point fault. And we we start by saying, can any given fault, any given stuck at in the system, lead to a violation of safety goal by itself? And if it can, if it, we look at that North Star and say this by itself can violate a safety goal, we call it a single point fault. And then we're going to line up safety measures to mitigate them, either prevent them or detect them, and bring the system to a safe state. And the fraction of them that we can't control are called residual faults that we have to minimize. And then what we do for all of the faults is we say, even if they can't lead to a violation by themselves, is there some other fault somewhere that might cause it to violate a safety goal? And sometimes these are faults in the safety mechanisms themselves, where if the safety mechanism breaks, the primary function continues to work, but that fault just sits there waiting. We call that potentially a latent fault if it's not controlled, because if a fault in the primary block now occurs, you would violate the safety goal. And so, we are obligated to analyze both single point faults and latent faults. And we do this with a variety of safety measures. And here's some examples. Of course, software also has safety measures, which I didn't really detail here, but digital and analog both have different kinds of safety measures that are commonly employed. A CPU might have a 1 out of 2 dual core lockstep or a windowed watchdog. Memory has, ECC and BIST. State machines can be hardened. We can check their state transitions. Communication pathways can be hardened. And in the analog domain, we might construct voltage monitors, clock monitors, or even do plausibility checks between related quantities. For instance, if they're ratiometric relative to one another, or if, say, one is a sine and the other is a cosine, we'd make sure, hey, do these look like they're relative to the same underlying angle quantity? And if not, perhaps detect a fault. So we do all this in order to meet metric targets for the types of fault coverage that we have to have. So let me introduce these targets. So they're defined by the standard for each level, ASIL B through D. ASIL A doesn't require you to have numerical targets, just follow the process. And they come in two kinds. One kind is a percent coverage. So the single point metric and the latent fault metric require us to detect or mitigate 90, 97, or 99% of single point faults and 60, 80, and 90% of latent faults. And that goes all the way down through the different levels of the hierarchy. But then the other metric, the PMHF, is a rate, the number of failures per hour of the entire system, which gets increasingly lower as the ASIL rate increases. And again, this is, one fit is per billion hours of vehicle operation. So for 100,000 vehicles with 10,000 hours lifetime, this equates to maybe one failure over the fleet of produced cars over its lifetime. And again, that's for the whole system. So if you're making a chip, you don't get all of that yourself. You make an assumption as to what fraction of that is allocated to you by your system provider. Now, the calculation of these metrics is done by a variety of techniques, analysis, but most commonly by fault injection. And I'll just briefly touch on what this is. Now, fault injection can be used in two ways. One is just to verify, does the safety mechanism work at all from a DV standpoint, but then also used to measure the percent coverage of those metrics that I just showed you. And as you might expect, what you do is you start with a simulation of a good machine with a good workload. And the workload might be for embedded software running in embedded cores, for instance, those interrupt handlers that I mentioned before, to make sure that you can expose a detected fault. And then for a list of faults, you're going to run them one at a time by injecting a fault such as a stuck at into the hardware, and then verifying, does it potentially violate a safety goal, and did the safety mechanism control it? And if it's been detected, that's great. But if outputs of the sim indicate that a safety goal might be violated, then a hazard might result, and we call that an undetected fault. And through the campaign, we statistically add up what those fractions were, and that forms part of our argument for the achievement of functional safety for that element. So this has been just an introduction to the basics, the whys and the hows of functional safety, and the life cycle. And you know, there are a lot of challenge in these which we'll go into in Jason's part of the talk. You know, having to do with the scale of products that we're developing, you know, in state-of-the-art vehicles and products, the differences between analog and digital. You know, analog fault injection is its own discipline, really, as well as digital, and the challenges of like managing large sim campaigns and times and so forth, and the requirements of the life cycle. But with this overview in hand, I guess what we'll do is we'll break at this point at the 20-minute mark, and then we'll turn this over to our co-speaker. So if you can unmute yourself, or if you can't unmute yourself, raise your hand and the moderator will unmute you. Let's see, where's the, okay. Any questions or comments? Does anybody have an experience they'd like to share with functional safety from their own experience, or from what you're anticipating a product development might entail? Well, in the absence of questions at this point, I think what we should do is then introduce Jason Campbell. If you could introduce yourself and take it away.
Sure. There's a note here from Alessandra, John, that seems like people cannot unmute themselves. So we need, I don't know how.
Yikes. Okay, so here's what you do. If you go to the participants menu up here, if you're a participant, you should be able to say raise hand. And then we'll see that in our version of this. So this is what I'm looking at. So like Alessandra, could you try this out by raising your hand? And we should see a little...
I just managed to unmute. So it doesn't work when you look at the phone. You have to go at the top right and then click mute, unmute.
Okay.
I was just clicking on the phone, so my mistake.
Okay, no worries.
Yeah.
So does anyone have a question? If so, go and unmute yourself that way. All right. So we're hearing your mic anyway, I think, Alessandra. Maybe that's Jason. But I think we're ready to turn it over to your half of the presentation.
Sure. Let me just figure out, how do I,
let
it
me
says share.
Right, so I'm going to stop sharing.
Okay. Then let's see. Screen 2. Okay, can you see my slides then?
Yep.
Okay. Hello, everyone. My name's Jason Campbell. I work in the Functional Safety Tools group at NVIDIA, and I'm going to follow on to John's presentation. He talked about the functional safety analysis, and I'm going to spend a little bit of time talking about how we then go about to verify that analysis. I create a really long title here because we're talking here specifically about SOC and hardware. However, the ISO 26262 standard is for all of systems, including software and everything here. So, you know, we're kind of very focused here. So let's move on. So first, I want to talk about, you know, what are the goals of functional safety verification? This may seem obvious, but you know what we want to do is verify the functional safety analysis. And just want to say that this whole functional safety process, we could probably spend a week trying to describe it. It is fairly complicated. We have just 20 minutes each here to do it. So what you're getting here is extremely high level, not a lot of detail. But what we need to do here is for verification is to verify the analysis itself. Part of that is to provide evidence that the functional safety objectives have been satisfied. And that evidence could come in the form of documents, could come in the form of tool reports, some kind of evidence. And there's many methods of how to do functional safety verification. I've listed a few here, and often you use more than one. Inspection is the primary method. So once you've got your analysis done, typically those analyses in the early days were done with Excel spreadsheets. Now we have tools, and you're going to take a look at those, walk through them. I'll talk just a little bit more in the next slide about inspection. John talked a little bit about functional verification for finding systematic hardware failures. So this would be, you've run code coverage, for example, and that's a form of functional verification that you can use to find the systematic failures. If we take a look at random hardware failures, we're primarily talking about fault injection, and that's what I'm going to spend the most of this presentation on. That's my particular area of expertise. Other methods you might use: prototyping, beam testing. That's really takes a look at whatever your design is, what you feel is appropriate for your verification. So let's take a little look at what is the goal of inspection, because this is our primary method of verification. So we have today, as I mentioned, we have a lot of tools which we can create our FMEAs, FMEDAs in today, and they do a number of automated checks. For example, if I define a safety mechanism, but I fail to use it or assign it to any particular failure mode, I expect my tool to flag that. However, there are a number of non-automated checks that the tool just cannot do. And so one of those, and perhaps the primary one, is to ensure the analysis is complete. So we take a look at and say, have we analyzed every possible failure that we can think of? For example, if we take a look at a state machine and we say, if this state machine fails because of the presence of a fault, it reaches an illegal state. Have we considered that in our analysis? And then, have we done the appropriate assign a safety mechanism and so on? So we have to look at each one of those. A typical SOC is going to have many thousands and perhaps tens of thousands of possible failures, depending on how large it is. Another thing we need to do is we need to do an analysis down to at least 3 levels of hierarchy. This is required by the standard, so we need to make sure that that's been done. Another thing is to take a look at all the evidence that you have, the documentations, and say, do we have an author, a version, a date, and a change history for all of those documents? So we've got to take a look at this and put a plan together and make sure we have a complete analysis. Perhaps the second most important thing is to ensure the analysis is correct. So we take a look at a particular failure mode, which is a way the design can fail. So if I look at my state machine and I say, well, have I assigned the correct hierarchy to that particular state machine or that failure mode, so that when I do the analysis, I'm going to be able to say, okay, I've run fault injection on it, injected faults in that part of the design, and this is the result I got. Same with the safety mechanism. Do I have the correct safety mechanism assigned to that particular failure mode? Finally, we're going to take a look and say, review all the documents, make sure they're precise, clear, well-written, easy to understand. This is all required by the standard. So we're going to do all this through just simply doing inspection, reviews with peers, and so on. So let's take a look at fault injection. John touched on it a moment ago, but it's a method to evaluate the effect at a fault on an observation point. Typically, an observation point will be your primary I/O, but it doesn't have to be. You can use an internal observation point, let's say a memory address, where you're computing a checksum, and you can use that. We have the underlying assumption that at some point you will read that checksum out to a primary output so we can observe it. So we do those kind of things to make fault injection more efficient. Now, John also talked about the types of failures. There's 2 types: systematic faults and random faults. So systematic, as John mentioned, is it's a fault that is occurring during the design. So it's a bug in the design. It's a problem with manufacturing. So it's something that you have to fix by changing something. Now, if we take a look at a random fault, a random hardware fault, this is a fault which occurs unpredictably through the lifetime of the hardware. And we look at two types of random faults: permanents, which are often called stuck at, typically caused by aging, and transient, called a bit flip or a single event upset, typically caused by a radiation particle. So these are the areas that we focus on in terms of with fault injection. Now, if we take a look at the number of possible faults, a typical SOC has millions of permanents and trillions of possible random, possible transients. So it's a really large number. So I'm going to talk a little bit about how we're going to deal with that in a moment. So if we take a look at the goals of fault injection. So when the functional safety analysis was done, an expert said that this particular safety mechanism is going to have an efficacy of 98% or whatever number that they gave it. They're also going to say that there's some faults which are safe. And what we're going to do with fault injection is we're going to verify the claims made by that expert. So if we take a look at a safe fault, that might be a fault which is a signal tied to 0. So a stuck at 0 is safe. Nothing can ever happen if that fault were to occur. There's actually not a lot of safe faults in a design. If you think about even logic, which you say is unused, a lot of people will call that safe, but it's really not safe because faults that happen in that logic could suddenly make that logic become active. And therefore, I think personally, there's no such thing as 100% safe. So, at NVIDIA, we make everything at 99. But then we also, we're going to measure that efficacy of that safety mechanism, verify that claim. What fault injection does not do is not verify that the design or the safety mechanism are correct. And John touched on this as well. We assume that everything has been verified by a design verification process, everything is good. It also does not verify the design at manufacturing. That again, it was done in the factory. It comes out of the factory. We assume it was 100% correct when it left the factory. What we're doing is we're trying to measure the effect of a fault which happens once that design is in use in the car. So the next, so what we're going to do first is to figure out what requires fault injection. So the way that we do this is we first eliminate which doesn't require fault injection, and parts of logic which are not safety related. And this can happen like we have performance measuring logic in our chips, and that's not safety related. If a fault occurs in there, it doesn't matter. And there's also many small failure modes which don't have a material impact on the failure rate. If we have a failure mode with an area of 0.001% of the design, it's not going to matter if a fault is in there. The other thing is, John mentioned this too, not all safety mechanisms require fault injection. If we take a look at ECC and parity, we know how these operate, we can predict what the results will be. Same with redundant hardware. We take a look and we go, okay, we know we have redundant hardware, we know what the effect of a fault is. The trick there, and John mentioned, is the common cause failures. Some safety mechanisms also cannot be fault injected. If you take a look at watchdogs, they typically require a lot of cycles before they trigger. So in simulation, we just can't run that many cycles. So we have to eliminate those, and we just have to use the estimate that the expert has given us in our calculations. And often a failure mode may have multiple safety mechanisms. So we may have a watchdog combined with something else. So we can take a 60% efficacy of a watchdog along with an 80% efficacy of the other mechanism. We find a way to combine those and come up with a final number. So when we eliminate what doesn't require fault injection, we're left with what does. So this is the complex hardware safety mechanisms, and they're really dependent on your design. So we have many complicated ones in our chip, but they're very special to what we do. Software safety mechanisms, same thing. So we have a lot of software checks that are being done, and we need to verify those. Then there's something called the software diagnostic library. So this is a set of software that we develop, or you would develop. You'd give it to your end user. They run it periodically, and then that will detect any failures. So if we take a look at, let's say we have a software diagnostic library that computes an image checksum. So we take a known image, we run that through our software diagnostic library, we get a checksum, we compare it to the known checksum. And we do that every millisecond or whatever it is appropriate. And if we find a failure, then we know, aha, we've got a problem. So let's take a look at now, what are the challenges of fault injection? So the first one's going to be the simulation model, and I'm going to talk about each of these independently. Fault classification, the stimulus, or sometimes called the workload, dealing with the large fault population, and then I'm going to touch a little bit on the tools available for fault injection. So let's start out with the simulation model. This is our very first challenge. So we can use an RTL model. It has some advantages that it's available early in the cycle. We haven't gone through gate level synthesis and so on yet. So we have it. Typically, it's already running in our design verification group. So we have some environment available, but it's less accurate. We can use it for transients because typically the flops and storage elements and memories in an RTL model are the same in the gate level model, or they're very close. It, however, cannot be used for permanent faults. The reason is that there's no way to map an RTL fault location into a gate fault location. A single RTL statement may generate 100 gates. So we have no way to map that single statement into 100 gate fault locations. So a gate level model is more accurate because it's basically what is going to be implemented in the silicon or very close to it. And it can be used for both transient and permanent. It also has an advantage as well when it comes to runtime. I'll talk about the runtime differences between these two models a little bit later. So the next thing is how to classify your faults. And John mentioned that there are three broad categories. My definitions are a little bit different than his, but it's the same thing. So observed faults, diagnosed faults, and safe faults. So observed faults are dangerous. So these are faults that when they're going to have some effect at an output. And so they have the potential to cause a failure upstream and something bad to happen. Diagnosed faults are observed faults, which are detected by a safety mechanism. So these are good. We've been able to detect them and move to a safe state. The last category is safe faults. Now these cannot be observed, so we don't have to worry about them. We don't have to fault injection run them. So one of the challenging things with fault classification is to figure out the correct observation and diagnostic checking. And this seems obvious, but it's actually quite complicated. The reason is if we take a look at looking at every IO, every clock cycle, that's very, very pessimistic. And so we often need to put a check on them. Let's take a look at an example here. So we're looking at every cycle on a data bus, and we see that a particular fault becomes observed because it all that fault did was, let's say, slip the cycle count by 3. So it showed a difference, but the thing is it didn't necessarily matter. So if we look at the final result, we got that final result maybe 3 cycles later, but that's within our tolerance, so that's not a problem. So if we call that fault observed, we may classify it as dangerous and not diagnosed, which counts against us. Now, if we use a valid signal rather than check every cycle, then we can say, oh, well, that fault didn't matter because when it was observed, the valid signal was not asserted, therefore we can ignore it as long as it was correct during the valid signal. So this is the kind of thing that you need to do. It's a little more complicated than it seems. And the more complicated your safety mechanism is, the more complicated this check is. I'll give you another example that proved very difficult for us at NVIDIA. So our CPU has predictive execution. So if we see a fault become observed during a predictive execution that is subsequently discarded for whatever reason, we still call that fault observed and dangerous, but in reality it isn't, because that execution was discarded and it will be redone. So trying to trap this and figure out this difference was very challenging for us. Let's take a look at stimulus. This one also is a pretty big challenge. So an effective set of stimulus is one that identifies a large and complete set of observed faults, because we want to observe faults, then we want to measure them to see whether they're diagnosed or not. So very often people say, well, I'm going to go look at my functional verification tests. That's where I'm going to get my stimulus from. However, what we find is that these are often very not effective, and there's a number of reasons why that's the case. If you're using random stimulus, typically the run times are too long for fault injection. They're also not very targeted, so you can spend a lot of simulation cycles and not get a very good result. And often the functional verification tests are written at the block level. But if we have a safety mechanism at a top level, like say it's a software safety mechanism, we have to have a full chip simulation. And the way verification is done, typically there's very few full chip simulations that are run because they're so long. So that's another challenge that you have. Another challenge, you have typically thousands or maybe tens of thousands of functional verification tests, and you can't run fault injection on all of those. It would take forever. So choosing a set from that can be quite difficult. You can choose a set, nothing happens, or you get very low, and then choose another one, and so on. So it can be quite challenging. There are tools to help with that, but still a challenge. So what I think is a better set of stimulus is a small representative set of application software. So obviously this is a CPU-based type stimulus, but if you then can run a small set, couple operations, the advantages are that these exercise the faults that are going to be relevant to the application when it's in use. So you can avoid a lot of other faults that don't matter. So I'm going to talk about filtering a little bit, but we use this to filter out a number of faults to get rid of the ones that don't matter. Also the software diagnostic library. So this is a little bit unique because it's both a safety mechanism and a stimulus. So for these software safety mechanisms, you're going to actually run the software diagnostic library as stimulus to measure how they react. So once you have stimulus, the next challenge is to figure out how to apply that stimulus. And there are two basic methods. The first is what's called the reactive test bench. And this is what you normally would have in your design verification. You just would have a test bench. So you're playing that stimulus in the test bench. And the reason it's more accurate is actually when you introduce a fault, that fault can cause a difference at the design IO. That stimulus then reacts to that IO change. I'll give you an example in a minute. The other thing is that your test bench, if you're using UVM or PLI or something like that, it's going to require a logic simulator, and I'll explain the difference of a logic simulator versus a fault simulator in a bit here when I talk about the tools. The other method of application is capture replay. In this method, you're going to run a logic simulation using your test bench. You're going to capture the VCD on the IO. Then when you go to use it for fault, you're going to remove that test bench, so you just have the DUT, and then you're going to replay that VCD file as stimulus. This has one disadvantage, which is mainly that it's inaccurate, because when the stimulus, it can't react to the presence of a fault. And so let's take a look at an example. So we're going to have an incorrect address, a read, due to a fault. If we have a reactive test bench, that will react. Let's suppose that the correct address is 123, and then we introduce the fault, and then that address becomes 323. When we have a reactive test bench, it'll correctly read the data from address 323 because it never sees the 123, gives that data back to the simulator, and then you get an accurate result. If you have a VCD replay, what happens is it sees the 323, but ignores it. It doesn't, it's not able to adjust to it So then it returns the address from 123. So it gives you a bad result. There's no way to know what the difference is between a reactive and a VCD test bench. There's no way to measure exactly what that pessimism or optimism is. It's just something that you have to take into account a little bit. So let's take a look at how to deal with these millions and trillions of faults. So we cannot run fault injection on millions of faults. It's just not feasible. The runtime wouldn't allow it. The good news is we don't have to simulate all the faults. So we take a look at what do we need to simulate again. So we use sampling techniques and we try to reduce the fault list down to about tens of thousands. That's a feasible number for us to simulate. We use confidence level interval sampling. So if we take a look and we say we have a confidence level of 99 and interval of 1 on 10 million faults, and we have a safety mechanism that is 95% effective, we actually only need 3,056 faults run in fault injection. So you can see this is a really important way to do this to get these numbers down. But you also have to get enough faults to get the statistics to work for you. So I recommend sampling per failure mode versus across the entire design. Both are allowed by the standards. The reason I prefer sampling per failure mode is because it distributes the faults according to the failure mode size. And by size, I mean gate count or area of the failure mode. And then this also avoids having no faults in smaller failure modes. So we want to at least say, we've got at least one fault in this failure mode of every failure mode that we're going to run fault injection on. So filtering techniques are pretty much an absolute must. So one of the filtering that we do is that we inject stuck-at faults on flops, and then we see which ones of those are observed, and then we use those observed faults to generate our transient failure list. So that's how we go from, I think I estimated in our latest design, we had about 150 billion possible faults. And then we got that down to, a couple 100,000 that we actually simulated. So this is definitely something that's really important on getting that fault list down. Let's take a look at the tools available. So software is the primary tool, and there's two classes that you can say there. A logic simulator, such as VCS, can be used for fault simulation. So it has an advantage that it's already working because it's your functional verification folks are already running this. It's pretty simple to use it for fault injection. It has a very significant limitation, however. You get one fault per simulation. And we take a look at an example. If we have to simulate 10,000 faults and each simulation takes 3 hours or 30,000 CPU hours, 1,250 days, and it's obviously not feasible. So we can speed this up a bit. We can use multiple CPUs. That's a single CPU per fault is called serial. When we use multiple CPUs, it's called parallel. So if we used 100 CPUs, we can get this down to 125 days, but that's still probably not feasible. So there are specialized products for fault simulations called concurrent fault simulators. Zoix is probably the most widely used, and it can run thousands of faults in a single simulation. So if we take a look at our 10,000 fault example, if I use 10 CPUs, I can run that whole simulation in 10 hours. It has some disadvantages. I mentioned like the capture replay system must be used, so no UVM, PLI, so it has definite limitations. Also, emulation can be used. Emulation is expensive, and it actually suffers from both the limitations of the logic simulator and the concurrent fault simulator. So it's not a great tool for fault injection. But if you want to simulate a long-running application, such you want to boot your application and run something, emulation is often the only thing you can use. Software fault simulator just won't run fast enough. Finally, there's static analysis, and there are tools that use controllability and observability analysis, just like in ATPG, and they try to give you a prediction of your fault coverage. The advantage of it is it's very, very quick. The disadvantage is that it is a prediction and it's not an accurate measurement. So let's take a look at all these challenges in a real world case, which is the NVIDIA Xavier SoC. So we had approximately 27,000 failure modes, of which only 10% required fault injection. And again, we eliminated all the ECC, parity, and those kinds of failure modes. We used a gate level simulation model. This design was already in production, so we had gates. So this is what we used for our fault injection. For stimulus, we used a software diagnostic library for permanent faults, and we used an application-based stimulus for transient faults. We spent approximately 3 months determining how to get the observation and diagnostic checking correct. Now, it seems like a long time. A lot of it is because when we ran a simulation, it took 3 to 5 days to get the result. And then if the result wasn't correct, we had to iterate on that. So it over time, it just took a long time to do. Sampling, definitely key. I mean, we had to use sampling and filtering to reduce our trillions of faults down to what we could manage in simulation, which is a few tens of thousands of stuck-ats and a few hundreds of thousands of transients. We used a concurrent fault simulator. For any particular stimulus, the runtime was from days to weeks, and we used hundreds of servers. So at any one time, we had maybe 500 servers running fault injection, and this went on for a long time. The overall fault injection effort took about a calendar year from start to finish. So this is a pretty challenging effort to do, for sure. So in summary, functional safety verification is about verifying the functional safety analysis. Fault injection is just one method of that can be used for functional safety verification. Primary method inspection. The goal of fault injection is to verify the efficacy of a safety mechanism, and it has a lot of challenges: simulation model, observation checking, stimulus, large numbers of faults, and very, very long run times. So if I have to give a summary to the summary, it's that fault injection is not always required, but when it is, it's very challenging, it's difficult. So we'll open it up to any questions.
So one thing I would like to ask if we could do is just perhaps to have a show of hands. As I see, we have a pretty full list of people here, close to 30 people. If you could go to the participants screen and just raise your hand, are you involved in a functional safety development now, or are you about to be? Be interesting to see how many of you might raise your hand to show that this is something that you're involved in right now. Can you find that in the Zoom UI? So the participants is at the bottom. Okay, I'm starting to see some hands. Sylvia, Peter, Misha, Svam. Good. Has everybody found that control? There's a few more. Excellent. And then if you want to unmute yourselves, if you have anything to share about what you're going through or a question you'd like to ask.
Maybe I start, Sylvia speaking. I'm working for Infineon Technology.
Hi, Sylvia.
Can you hear me?
Yep.
Yeah, okay. Yeah, we also had the first ISO project, but I was in charge of analog fault injection. So really do this kind of part of the verification here. Maybe another question, which was a lot of work in addition to this verification, was the documentation. Because yeah, you have to be, it was mentioned in one of the talks, I think also here, that you have to spend more effort on the verification, that it's fine for the ISO 262. And did you use, for instance, automatic generators for to generate a document on this?
So this is John Hayden. It's
Yeah,
great to get
John.
your question, and from Analog Devices, it can respond. So another follow-up: was this the first time your team did anything with functional safety, and had they been using some of the other practices like requirements management systems and document systems before, or did they have to kind of learn how to do that all at once?
Yes, of course. We had documentation systems, but there it was very specific. More requirements or more description needed.
Yeah. So a
yeah.
lot of times a group, has not yet used formal requirements management systems with traceability tools before, and they're learning how to do those at the same time. So I don't know if that was an issue for you, but analog fault injection is a discipline of its own. We do it at Analog Devices, of course. The general technique that people use here is instead of in the digital domain where you would go down to the gate level, as Jason described, and identify a logic cone of similar faults that all lead to the same, say, flip-flop that might stuck high or low. For analog, what we would do is break things down to, say, a block level, a comparator, a reference,
exactly.
an amp, and then hit the ports of that. Was that your experience as well?
Yes, we do it as well. To do it, this was the strategy, to do it on lowest level possible. And in analog, sometimes you can break it down to voltage generators also. Well, it's the faults are more clearly described here in the FMEDA.
And cool. Did you have a specific question about analog fault injection? The question that we could answer or discuss?
No, was more about how you can do then later a nice report.
So Sylvia, at NVIDIA, we do use some automation for the report generation. So we use some requirements tracking tools, and then from there we can generate reports. As far as the FMEA, FMEDA itself, those come from the tool that we use to develop those. And then we also use a lot of white paper type documentation that people are writing by hand to justify how their safety mechanism works and what the efficacy is of that safety mechanism.
Okay. Yeah.
So I think it's pretty common to do the things that you're probably doing with the requirements management tool, say to export your requirements or do traceability reports on your requirements.
Yeah.
But what we do at ADI is we manage all of the work products in our requirements management system. So not just the text of the requirements, but also the specification documents, that are then traced back to the requirements that gave rise to them. The V plan is imported into the RM tool and linked through, the traces back to the requirements that they verify. And I don't know if you do the same, but then this allows you to use the RM tool to automate to make some of those arguments that, for instance, there's a requirement for every test, there's a test for every requirement, and so forth.
Yeah, in principle, we are doing this as well, but in the end, when they always argue that you should deliver somehow like a PDF document where everything is covered. I don't know if it's a must. Yeah.
So when you sit down with a customer or an auditor, they're definitely going to need to have some fixed tangible form. So you'll want to do a PDF export from your RM tool. And sometimes, at least what we find when we're being audited or presenting, is it may help to bring up the RM tool, this is all under NDA, of course, if they want to drill down. If you're in an...
Yeah, exactly. This what we also had, and sometimes that the traceability in a PDF is no more that good.
right? So
Yeah.
what you end up
Exactly.
having to do is you say, here's the text as a PDF, and then here's a traceability report. You know, our tool can generate it. It's a commercial tool, JAMA, can generate a table. And then, you know, if the customer or the auditor wants to drill down further, you know, they might invite them to you know, come do this securely and say, start at the safety goal, drill down. Because that's what an inspector does. Just generally for the audience, there's two kinds of verification in the ISO term of there's inspection and walkthrough. And in a walkthrough, it's, you know, you have a presentation, you go through your PowerPoint deck or whatever, your screenshots, but it's really the developer is the active party. In an inspection, it's the other way around. You know, you put your material ahead of time for the inspectors to review, and then they ask the questions. It's like they're a prosecutor in court. You know, they say, I want to see what you have for this, and you follow that wherever they want to go. And the value in that is that sometimes they'll have a perspective that you don't, you know, that's their job as an inspector to feel that they've adequately sampled the design and kicked its tires, so to speak, enough to sign their name and say, I've verified that it's complete and consistent. So that's ISO verification. Now, are there anybody else with a hand raised that wants to jump into this discussion or has a question?
So thank you, John and Jason.
Okay. Anybody else have a perspective on what Sylvia is doing for that matter? Just remember to unmute yourself.
Jason, John,
Hello.
one question from my side, actually.
yeah,
Oh, go ahead.
No, please. You were first.
No. I just wanted to kind of wrap up with a viewpoint, but go ahead. And I don't know if we have a hard stop. I don't know from the moderators. Can we go ahead a few more minutes on the moderator side?
Yeah, that's fine. You can go ahead. Yeah, I just confirmed.
Thank you.
Great.
You can go ahead. No problem.
Yeah, the advantages and disadvantages of being at the end of the day is you've got as much time as people are interested in sitting around and wanting to chat. Thank you. So, Jacek, over to you. You had a question.
Yeah, hi. My name is Jacek Rosiak. So I work in Cadence in Poland. So actually, I have a very specific question about what Jason said about fault injection in ECC and parity. So you said that you are not doing any fault injection in these. So my question is that in the design we can have like parity or ECC checkers and parity and ECC generators. And are you fault injecting in these blocks, or I'm not sure exactly what you meant that you don't do fault injection in parity and ECC.
Yeah, we actually, for the memories, we break them out into two pieces. We break them out into the core memory itself, and then the memory around that. So, the logic around that. So this would be your address decode logic, and would be your ECC, and your parity is, you know, all that logic is broken apart. So we don't do any fault injection in the core memory logic itself for ECC and parity protected memory. For the other logic, such as the address decode, you know, we can fault injection do fault injection for that, and the ECC, we can also do fault injection in that. A lot of times it's not done. We simply go with an estimated value for those, but that's how we do it. We do break it apart.
Remember that there's many different ways of carrying out what ISO calls verification. In other words, making an argument for the efficacy of something. You can do it by fault injection, by simulation, but you can also do it by analysis or by reference to state-of-the-art, you know, handbooks and other published sources. So, for instance, if I've got an ECC block or a communication link, a serial link that's protected by some sort of CRC, I can do an analysis, I can show my math and say, based on this, I can detect 100% of, I can mitigate 100% of single point faults and detect all of the dual point faults, or my CRC Hamming distance. And I don't need to simulate that, because I could simulate every single fault and it's just gonna, you know, come back to what the CRC handbook said it was. So, you know, you make a statement as to why you chose that kind of method of proving your point, and then go do it. But you know, fault injection has its place when the circuit is not easily analyzed. You know, so for instance, the ECC tree, you know, we could fault inject that in its entirety or sampled. But maybe all you need is to say mathematically, here's the polynomials that we used. We can do a formal proof. We actually didn't make a big point of this, but you can use formal tools to prove that all of the gates are observable, and that works too. And then maybe what you do is you just, from a DV standpoint, fire off 1 or 2 faults into that and verify that that safety mechanism did fire. And just to make sure that it's been integrated properly into your design hierarchy, which is another place of possible slip-ups. Did that help answer your question, Jacek?
Yeah, I think so. Yeah, okay, thank you.
If there aren't other questions, maybe just to kind of wrap it up, we do have a functional safety working group, you know, within Accelera. John, Jason, does anybody want to share, or, you know, either one of you or together, what are some of the things that we're trying to address about functional safety in the working group that might be a good summary of, you know, what are some still of the open questions or challenges for this group?
Sure, I'll take a shot at that first, and Jason as well. So the point of this functional safety working group in Accelera is to recognize that we have lots of different work products and you know, CAD tools and safety analyses that have to be managed. And in any development organization, there's, you know, there may be multiple levels to it. You might have multiple companies involved. I might have subcontractors supplying IP to me and then me to my customer. And today there aren't a lot of standard formats or interchange for this. And we have to do a lot of hand-built adapters to talk between various tools. So the goal of the functional safety working group is to unify all of that, to create standard data models of what is the information that that you're going to want to represent, and then how might we encode that in files with some sort of language reference or standard protocol for inter-process communication if I'm piping things between 2 tools that I'm using simultaneously, so that we can look forward in a period of time, a year or 2, when these tools come out that respond to this standard, that any of you that are working with any other companies or even people in your own company can expect that the tools that you're going to use will allow you to all work together, you know, in similar framework, much as we have standard formats for layout and for RTL and for UVM and other sorts of, you know, power management and so forth. Today, this is a barrier that gets in the way of innovating together with customers, you know, early simulation development of concepts at tier 1 or OEM, and model-based system engineering, for instance. And we hope that we will get to that future soon, where with the work of this standard that we can all work together a little more smoothly. And Jason, what's your take on this and the experience you have with the group?
Yeah, just mention that actually this group is a sort of underneath the umbrella of a new IEEE standard, proposed 2851, and that standard you know, goes to address some broader aspects. But yeah, within Accelera, we're focused on how to exchange the data both laterally and vertically. So when you think about if we're building a chip and we have to give that to a system builder, you know, we have 27,000 failure modes. well, we need to break those down or collapse those down into 5 failure modes or something to give that to the next level. So the interchange stuff is what Accelera is focused on. Yeah.
Thank you so much. Any other questions from anybody?
And I see we still had hands raised from Philip and Liu and Mihai. Do either of you have questions you'd like to ask at this point? Okay.
Maybe these were
That's from the question
functional safety
answer.
poll.
Yes.
Yeah.
Okay. Back to you, Alessandra.
Okay.
Oh, yeah. Peter.
Yeah. Hello. So we were talking about the simulation models and how the gate level simulation model was better than the RTL simulation model. Since there are tools like LEC and Formal, is there any way to back annotate the faults from the gate level into the effect that they would have on the RTL model?
No, that mapping is just not possible either way, from the RTL to the gate or the gate back to the RTL. The best you could do would be to say, so here's a block, and then within that block you had a collection of faults. It's the best you could do, but yeah, you just can't map it. And then the RTL, if we take a look at fault simulation in particular, like with RTL, some people always think, well, RTL is faster to fault simulate. It's not necessarily the case. The gate level, the concurrent fault simulator operates way more efficiently at a gate level. It's based on the fact that faults tend to have very localized changes, and that's how it can do more faults. But RTL or Formal, Formal has the challenges of dealing with larger designs. So if you have a safety mechanism that's very local to the block you're going to analyze, you could possibly use Formal. But if your safety mechanism is a broader scope, we have many cases where we break our design down into IP blocks, IPs, and then the safety mechanism actually is in a different IP than the failure is in. So we have to build DUTs to encompass all of that. And I think we get to the point where Formal just can't deal with the size of the designs that we would try to feed it. But RTL is useful in fault injection early on, because you can inject faults on the flops, you can inject faults on the IOs of your modules that you have, and you can get some sense. We do that. We do use the RTL model early on our next project here because we don't have gates yet. And then we actually use a low effort synthesis for the fault simulations at the gate level as well. So maybe more than you asked for, but hopefully I at least answered what you asked for.
Yeah, all very informative. Thank you.
And it really comes back
Jason,
to...
John, I think...
Yep.
Yeah, go ahead, John. I was trying to wrap up because I think we are a lot over time.
15.
And I think it's, yeah. Anything else quickly that you wanted to add?
Just wanted to say thank you to all of the attendees that came to our talk. We really appreciate it.
Yes, thank you, everyone.
And thank you, John. Thank you, Jason. This was really, really good. And we'll see you next time. Have a good day. Bye.
Okay.
Bye-bye.
Bye.